Hi, today I'll be coding something else for the random stuff code pen challenge. Last time I coded a random uniform distribution of dots all across the surface of a disk, as you see right here. That included how to avoid a common mistake that results in middle clustering, as you see right here. Today we'll be spicing things up, going from 2D to 3D, and we are going to code a random uniform distribution of dots all across the surface of a sphere, and then a random uniform distribution of dots throughout the entire volume of a sphere. The first 3D case, where the dots are strictly on the sphere's surface, is pretty similar to the 2D case, where the dots are only on the boundary circle, but not inside. And the second 3D case, where the dots are distributed throughout the entire sphere volume, is similar to the 2D case, where the dots are distributed all across the disk surface. Now, if you haven't seen the previous video, then 1, I am going to be linking to it in the description, and 2, I am going to start from scratch today so that you can follow even if you haven't seen that video, which you should see because I think it's pretty interesting, this part, how to avoid middle clustering. Anyway, let's get started, and we are going to begin by creating that sphere element. So if you've seen my previous videos, then you know we cannot do this because it's going to result in an error. We need to do it a bit differently, so we're going to have a div, and that emoji is going to be the value for the class, so like that. However, we can set dot emoji in the CSS. So for example, we can have transform style preserve 3D. This is going to be really useful for having 3D transform children inside this 3D transformed sphere element. If we didn't set it, the default value is flat, so all of its children would get flattened in its plane, which is not what we want. Now, if you've noticed what I said 3D transform children, which means that we cannot apply the same tactic as for 2D, where we use box shadows for those dots. Box shadow is strictly 2D, and it's not going to cut it for 3D. So we are going to have a number of dot elements. So let's say that's going to be 200. It may not be enough, but I don't want to risk a browser crash at this stage. So we're going to have, while n gets decremented and is still positive, we create our dot elements. Now in the CSS, let's put them on the screen, make them visible. Set padding, 3 pixels. Background, let's make that black, is too ugly. This is ugly too because we can't see where one element ends and the next one begins. So we're going to set border radius 50%, and that's going to help with differentiating between them, but it still looks really ugly. So we're going to do something I do often. So HTML body div, set display grid on all of these, and if I could type, that would be great. Okay, now next we are going to want to have actual dots, not that ugly thing there, so we're going to use place self center. The default is stretch, which is why they appear stretch initially. Okay, now we can see those dots, but we want them all stacked one on top of the other. We want them all in the same cell, so basically the sphere grid is going to be a 1-cell grid, 1 row, 1 column. So here we're going to have grid area, first row, first column. They're all placed in that cell at the intersection between the first row and first column. Next up, on the HTML, we're going to make this full height, which in turn is also going to make its contents full height. And we can actually move that place center on the sphere right here, right? And we can also set a few things on the body. So for example, background, something like that, and also a perspective. This is going to make the dots that are closer to us in 3D appear bigger, and those that are further away appear smaller. So let's say something like 15 ems, and let's also set overflow hidden, and let's also set a box shadow here. They're all stacked So it's going to look hideous at first, but now let's move on to distributing these dots in 3D. So giving them a translation, a 3D translation, and we are going to use individual transform properties because that's going to make it easier. We're not, if we want to animate the entire sphere, we're not going to need to have two different sets of keyframes, and another option would be not to have two different sets of keyframes, but instead add pseudo elements on each of the dot elements. So neither of those is ideal. So we're going to go with individual transform properties. Although I believe these are still not supported without a flag in Chromium browsers. I do have the flag enabled, and I am going to detail in the description how to get it enabled. Okay, so here in a style attribute, we are going to have that 3D translation. But first, we need to get those 3D coordinates x, y, z. Now, for points on a circle, right, we use polar coordinates. And in this case, if the points are just on the outer circle and not inside the disk, the radius stays constant. It's the radius of the circle. The thing that varies is the angle. So this can go up and down, right? And if we want to get the coordinates of this point, we use the fact that this being the projection of the radius on the horizontal axis, that angle is 90 degrees. Again, for the same reason that angle is 90 degrees. That angle is 90 degrees because it's the angle between the axis. So this results in that angle being 90 degrees. So this is a rectangle, which means that opposing edges are equal. So this y projection equals this. This is also going to be y. But from this right triangle, it results that it's the radius times the sine of this angle. And then the x-coordinate is the radius times the cosine of this angle. And you can see the formulas there, you can see the computations and all of that. Now, the 3D equivalent of polar coordinates is spherical coordinates. Okay, now there are multiple conventions for this. You can see how phi is that angle there, and here it's denoted theta, and that's phi, and yeah, which is theta there. It doesn't really matter. It doesn't matter what convention you use. It doesn't matter what you call those angles. You can call them Simba and Nala for all I care. As long as you can visualize them and you know how you place them, it doesn't matter what you call them. It doesn't matter which ones you use them, in what direction they're going. Because honestly, in CSS, the axes are completely different. This, for example, is the y-axis, the vertical axis is the y-axis, and it's pointing down in CSS. So that would be the minus direction, the negative direction. And in CSS, I'm going to want to consider the angle starting from the horizontal plane to the radius. So it's not going to start from the vertical axis to the radius. It's going to start from the horizontal plane, right, to the radius. And this direction upwards, which is the opposite of clockwise, which is positiveness in the CSS, this is going to be the negative direction. So an angle going up from the horizontal plane is going to be negative. But actually, let's make all those changes, like this. Let's make all those changes right here. Okay, let's make all those changes right here in the SVG. It's nice having an SVG to modify, isn't it? So that is actually going to be the third axis. Let's expand that, right? And then here we are going to have the x-axis, right? And the vertical axis is the y-axis. And that's actually the negative direction. Up is negative. Okay, now also I said that I want my phi angle to be this angle from the horizontal plane to the radius, which means that this is going to be phi minus 90 degrees. So let's get that. Okay, so this is going to be minus 90 degrees. So yeah, sometimes it's complicated getting some characters. Okay, minus 90 degrees. Okay, so that is my angle phi. Now, using this notation, so that's my angle phi, that's 90 degrees because that's the projection of the radius. Okay, this means that this vertical edge is going to be equal to the y-coordinate. So the y-coordinate is going to be the radius times sine of phi. Then this projection onto the horizontal plane is going to be the radius times cosine of phi. And this is going to be the hypotenuse in another right triangle. So if we project this projection onto the x-axis, right, that gives us the x-coordinate. So that's going to be the angle theta, okay, right, because we can also use this triangle, right. This is also going to be equal to the x-coordinate. So the x-coordinate is going to be that projection, which is the radius times cosine of phi, and then it's going to be multiplied with sine of theta. Now this other projection is going to be this projection onto the horizontal plane, which is the radius times cosine of phi times cosine of theta. So let's put that into code. We are also going to set a radius, and this is going to be 9 ems, and it's going to be fixed because we only put the dots on the surface of the sphere. So at first we are going to have two random numbers between 0 and 1. U is going to be a random number between 0 and 1. Then we're going to have a second one. This one is going to be V. And then we are going to get our angle theta, which is going to be so this angle theta goes from 0 to 360 or 2 pi. So we're going to have 2 pi times that u random number. So this is going to give us an angle that's anywhere between 0 and 2 pi. Okay, similarly, we're going to get something for phi. Except in this case, this angle is going to go from minus 90 degrees to plus 90 degrees. So it's going to be a 180 degrees or pi range. So we're going to have pi times V minus pi over 2, 90 degrees, which is the same as 0.5 times pi, right? And we can bring out that pi in front, and we're going to have something like that. And now we're going to have our x, y, coordinates. So here we're going to have the radius times cosine of phi times sine of theta, and then similarly, except it's going to be cosine, and yeah, of course I was supposed to change that, not leave it x. Now y doesn't depend on theta, and it's going to be sine of phi. And having done this, we are going to have translate, and we're going to interpolate those values, x, m, y, m, and this should give us the 3D distribution. And you can see how some dots are bigger because they're closer and others are smaller because they're further away. Okay, so that's something that we wanted. And let's say we're going to add some animation. So we're going to have keyframes. And this is going to go to a rotate Y1 turn. And here we're going to have animation, 8 seconds, linear, infinite, right? But we don't like how we see those dots from the side, so let's fix that. Animation, inherit, and then animation direction, reverse. So it's going to look kind of like that, and this looks pretty good, except can you see an issue? We don't have that many dots, so it's not that obvious. But if we, for example, double the number of dots, then it becomes more obvious. We have clustering at the poles, so please don't crash, please don't crash, please don't crash. Okay, now it's a lot more obvious. We have clustering at the poles, right? And this is because of this phi angle. So that is the issue. We have more points clustered there, and we can fix that by using something slightly different. So let's open that parenthesis, and here we're not going to have pi times v. We are going to have something slightly different. So we are going to have the inverse of the cosine, arc cosine, of 2v minus 1. So if v is between 0 and 1, 2v minus 1 gives us something between minus 1 and 1. And you can see how we have a much nicer, much more uniform distribution now. Look at it, much nicer. I think that's a bit too many elements, so let's reduce the number of elements yet again. And I'm going to show you what's the deal with the inverse cosine function. So let's go to this graph right here. So that's precisely the function I've showed you there. So this is defined on the -1 interval. And one thing I want to show you here, so we basically want to reduce the density at the poles, so at the ends of the function. And as you can see here, the difference between -1 and -0.9 is the exact same as between -0.1 and 0, right? So it's 0.1, the difference between those 2 points. However, the difference between their values on the curve, you can see the difference between those 2 values on the curve is much bigger than the difference between these 2 values on the curve. So we get a random number there, but it's less dense at the ends, it has lower probability at the ends and higher probability in the middle. And that's how we are compensating correctly so that we have a uniform distribution all across the sphere and we don't get that pole issue. Okay, now we can start from this, right? So we are going to take this and have it here, have pretty much the same CSS. Right? Okay, and we're getting that result. And we are going to want to have dots distributed throughout the entire sphere volume. Now, this means that we are going to have to vary the radius, just like we varied it here, right? When we wanted points all across the disk surface. So we're going to have to also vary the radius. So we're going to introduce another random number between 0 and 1. Actually, there's one thing I should have done here before copy pasting. So let's say that we're going to have a precision that's going to be 2 decimals, right? And all right, we are going to want to round to that precision, and we want that to be a number, obviously. So that's going to look a lot nicer. Okay, so now we're not going to have a ton of decimals anymore, which is great. That's what we wanted. Okay, now let's paste that, and I said we're going to have a third random value there. Let's call this W. Okay, let's increase that, and yeah, we are going to have a radius that's varied again. So here, this is going to be the radius times W. Okay, so now we are going to use that varying radius that's anywhere between the sphere radius and 0. So let's see it. And you can see that we have a problem. It's not that obvious when we have only 200 dots. Maybe it's more obvious if we increase the number to something like 500, but you are going to see it. And you can see it, that middle clustering. It's pretty much the same mistake that we had here with middle clustering. And here, let's expand this one right here. Now you can see how the difference between the current radius here and the current radius here is, here we take the square root of that random value between 0 and 1. So in this case, we take the square root because the area of the disk is pi times the radius squared. Now for a sphere where the volume is pi times the radius cubed, yeah, and then there's also division, but that doesn't matter, that's a fixed constant. So we are going to use the square, not the square root, we're going to use the cubic root. Let me just show you that. So here we have the square root, right, highlighted there, and then the cubic root. And it's precisely the same idea. You can see how the distance between 0 and 0.1 is the same as the distance between 0.9 and 1. But the distance between the value at 0 and the value at 0.1 is a lot bigger than the distance between the value at 0.9 and the value at 1. And the distance becomes more pronounced for the cubic root. So here we are going to use the cubic root of that. So like that, and we are going to have a much nicer distribution. You can see, looks more like a sphere. Let's risk and increase the number of dots. Please don't crash, please don't crash, please don't crash. Is anything happening? Please don't crash. Okay, it didn't crash. So yeah, this looks a lot more like a sphere, and I'm not going to torture it any further. It has a lot of elements. You don't want to know how many times I've ran into trouble recording this video, and yeah, everything crashed because of too many elements. So I'm not going to tempt my luck now. I'm going to end the video here. I hope you've enjoyed it. And if you like my work, if you like the work that I'm putting out for about a decade now, and you want me to be able to do more in the future, please consider supporting it. You can do so by being a cool cat and becoming a patron on Patreon. The link is going to be in the description. Or if monthly support is not your style, there's the option of a one-time donation. Again, the link is going to be in the description. Or you can make the stray cat happy with a gift of her wish list. Again, the links are going to be in the description. Or you could at least share this to show the world what can be done with CSS and mathematics these days. Because honestly, I think it's pretty damn cool. In any event, thanks for watching, and I'll see you next time. Bye!